Hey guys, welcome back. Today we will discuss the transformer architecture. In the last two videos, we looked into generative AI and its applications. We also touched upon the foundation models and large language models concepts. We saw that all generative AI models, be it ChatGPT or Gemini or Llama, all are based on one single architecture called transformer. So we will dig into that architecture today. Before going into that, let us understand the older architectures for solving NLP tasks and the drawbacks for those. Hope you all know that RNNs and LSTMs are the first models developed for NLP tasks. They are basically designed for sequence prediction. They work very well for shorter sentences, but they fail to capture the long range dependencies. That means they don't work well for longer sentences and paragraphs. This is how an RNN looks like, and this is how LSTM looks like. So they actually do sequential processing. So one by one. So if you give a sentence to it, it only processes one word at a time. So the first word will be processed and then it will give the next word and the next word will go next, next like that. So it's a sequential process. Same is the case for LSTM. So that's why these are very slow. At the same time, they don't work for long range dependencies because as it is sequential in order, by the time it reached the last sentence, it might forget about the beginning sentences. This is just like vanishing gradient problem. Let us see that by an example. Let us take this sentence. The scientist who won the prestigious award after years of research and dedication in the field of quantum physics is admired by many. Now, the main subject is scientist, okay? And the important here is admired by many. Admired is the main important verb here. Now, there is lot of distance. There are lot of words in between the scientist and admired. We all know that scientist is the guy who got admired, right? Now, due to this long distance between scientist and admired, RNN or LSTM may struggle to find this connection because RNNs process each word one by one, right? Like this in sequential order. Now, the gradient values shrink over the long distances. This will cause the scientist to be forgotten by RNN. Okay. By the time the RNN reaches the admired, it might forget the context about scientist. Okay. So LSTM also is slightly better than RNN, but it is not perfect. Even LSTM also uses a fixed memory, so very long sentences is still an issue. It leads to information loss. Now what happens is, because it forgot this scientist word, it might think like quantum physics is admired. So it changed the whole sentence meaning, right? So this is the main challenge in RNNs and LSTMs. Okay. So these are some of the challenges in the NLP. We discussed this in the last video as well. So it is unstructured data, highly unstructured compared to computer vision or tabular dataset, and it has a lot of variations. And RNNs and LSTMs are basically sequential computation, so it's very slow. As RNNs and LSTMs are failing for long range dependencies, there is no transfer learning concept because transfer learning concept comes into picture when you have pre-trained models. What are pre-trained models? Pre-trained models are models which are trained on large corpus, right? If you want to train a model on large data set, that is a problem because we are having sequential computation in the first place. And second thing is, even though we are providing large corpus, we might not be able to understand the context fully with the RNNs and LSTMs. So by empirical analysis, they identified that RNNs and LSTMs fail if the context length is greater than 30 words. So 30 words is very less, right? So a paragraph can have more than 100, 200 words. So training a model with large corpus is impossible or difficult with these models. There is no point actually. So before transformers, RNNs and LSTMs are used for task specific training. So let's say for sentiment analysis, there will be a separate model which is trained from scratch. Similarly, for another use case, there will be a model which is trained from scratch. There is no transfer learning concept before transformers because there are no pre-trained models. There is no point in training with large corpus and keeping the weights. It could never understand the whole context. See, pre-trained model is not task specific. Usually, these are very big models which are used for understanding the domain as a whole, just like ImageNet models, right? The classification models which are trained on ImageNet. ImageNet is a huge dataset in computer vision. The models which are trained on ImageNet understands the image domain as a whole. They can understand what sort of objects are there in the day-to-day images. similar kind of model if you want to train, the models are not capable of performing such kind of training. So there is no transfer learning, there is no pre-training before transformers. Okay, these are some of the challenges. So along with these challenges, there is a challenge in understanding the context itself. So if you see this example, the cat drank the milk because it was hungry. When it said it was hungry, this it is referring to the cat because cat was hungry, right? But the single word replaced by this sweet. In this case, the cat drank the milk because it was sweet. When it was sweet, that means the milk is sweet, right? So the higher weightage went to milk. So depending on even the last word or single word itself, the context will change. You might have read some novels, right? In novels, usually the character references comes at different points, referring that he or she like that during the conversations. That can go up to pages, the references, right? So if your models are struggling to just capture within 30 words, then how will they capture the context which are in multiple paragraphs? That means in between there are hundreds of words. So this capturing context is very difficult in case of RNNs and LSTMs. Okay, so now we have these challenges. We need to create a new model to solve those problems. So the first thing is we need to be able to capture large context length. Okay, at the same time, the computation should not be sequential. We should be able to do parallel computation so that any number of words or paragraph you provide, everything should be processed parallelly. So it can be scaled easily. So these points actually enables pre-training and transfer learning, because if you are able to capture large context lengths at the same time, any amount of data you give, if you can compute parallelly, then you can do the pre-training with large corpus of data, and you can use that pre-trained model for transfer learning later. Okay, so these are the objectives for the new model. Now we need to build a new model which have these features. Okay, then the transformers were introduced from Google Brain. So it was first introduced in 2017. It can capture dependencies for long range. At the same time, it can do parallel computation. So both of our problems it is solving. So the actual title of the paper is Attention is All You Need. Attention is a mechanism which is used in the transformers. We will look into that. So it just told that attention is all you need. This is the title of the paper. And it is a major breakthrough in the whole NLP and generative AI fields. Okay. Now let us understand this architecture step by step. Suppose I want to use transformer for machine translation. So this is the input sentence I gave and the output I need in this language. Assume that it's a black box. I don't know what it is yet. So this is a simple task. Now let us go one step further. Inside this transformer block, there are two major components. One is encoder, second one is decoder. So inside the transformer architecture, there are two modules. One is encoder and second one is decoder. It is not like you have only one encoder, you can have multiple encoders as well, like it is shown here. You can have multiple encoders, you can have multiple decoders. Just like how our convolution layers can have multiple convolution blocks, right? In case of computer vision, a CNN can have multiple convolution blocks. In the similar idea, in the transformer, you can have multiple encoders and multiple decoders. It depends on the complexity of the problem you are solving. If only two encoder blocks are enough, that is fine. Otherwise, you increase the number of encoder blocks. So that will increase the complexity of the model, which can solve complex tasks. Okay. Any model cannot take the text information directly. We have to convert the text into a numerical format, right? That is why you have an embedding layer. An embedding layer usually takes the input text and creates the embedding vector. So it actually gives embedding vector. So this vector is of fixed dimension. The common dimension is 512. Okay. So the input sentence is converted into the equivalent embedding vector, which is like this. It is an equivalent embedding vector of maybe 512 dimensions. This 512 is just an example. Okay. Because any architecture, it cannot accept the text as the input. So you have to convert that into equivalent numbers. So this is actually numerical representation. Okay. Now, what exactly is this embedding layer? So if you look at the NLP tasks, this concept is not new, converting the text into embeddings or equivalent numerical representation, because even for RNNs and LSTMs, we need to convert the input text into the equivalent vector formation, right? Usually the simplest methods are one-hot encoding, unique numbers, bag of words, TF-IDF. These are some methods used for converting the text into the equivalent numbers. Okay, so that means each word should have a unique vector which represents that word. Okay, every word should have unique vector. For example, if you take an example of the cat sat on the mat. So if you see, there are 6 words, but how many unique words? 1, 2, 3, 4, 5. So 5 unique words are there. Okay. So these for every word, like for the, for cat, for sat, for on, and then mat. For every word, I need to create a unique vector. Okay. For giving the model input. This unique vector can be generated by one-hot encoding or unique numbers or bag of words TF-IDF. Bag of words or TF-IDF are the commonly used ones because one-hot encoding and unique vectors are not feasible methods. I'm not going in detail into these methods because these methods are very basic methods. These topics are out of scope, at least for our discussion now. Okay. Now, the major drawback in all of this, as a common, we can say that there is no semantic learning in any of the above methods. Each word is represented as a vector in all of these things, but the semantic meaning of these words is not captured in this vector. It is some unique representation for this word, but it doesn't mean that this vector understands what cat is, right? There is no semantic meaning or semantic learning. Okay. So to solve this problem, we have an embedding layer. Even embedding layer is not new in the transformers. It is also there in the previous architectures. Embedding layer is nothing but a lookup table. It's a fixed dimensional vector. Usually we use 512 dimensions in most of the common architectures. So it's a fixed dimensional vector and it captures the semantic relationships. Okay. As it is capturing the semantic relationship, it can actually generalize for unseen words. Suppose if you are using this, in case of previous methods, whatever the words you have seen so far in the training, only for those words you have the representation. What if there is a new word came which is not seen during this conversion process? Then the models won't be able to do that. So, but the embedding layer can generalize for unseen words because this is a trainable layer. It can understand the semantic relationship, it is trainable. So that's why you can actually generate the embeddings for even unseen words. Okay. Usually when it is a trainable thing, that means initially it will be assigned a random value, right? Suppose I have 3 words. So I'm taking the example of king, queen, and apple. And I'm taking the dimension as 3 for the embedding. So that means there are 3 entries in each vector. So for king, let's say this is zero point 0.5, 0.2, and 0.1. For queen, it is 0.3, 0.6, maybe 0.8. For apple, it can be 0.9, maybe it can be negative also. So minus 1.2 and 0.4. So these are randomly initialized before training. We are saying the embedding layer learns the semantic relationships. That means the king and queen, these words, the vectors of these words should be similar by the end of the training, right? Something like for king, it can be zero point 0.8, 0.3, 0.2, something like that. For queen, it can be maybe 0.76, maybe 0.32 or something like that, or 0.24 like this. And for apple, it should be different. Maybe it's like 1.1, 0.9, and 0. Some 7 like that. So these are after training. These are the random values before training. So what I mean by that is, as it is learning the semantic relationships, the embedding vectors which are coming out from the embedding layer can represent how relevant the words are, how relevant different sentences or words are to each other. So it can give some understanding. Okay. So the embedding layers will generate the embeddings which have semantic information. Now let us look at the transformer architecture with this embedding layer. Now along with the embedding layer and the encoder decoder, there are some other additional layers which is like fully connected layer and softmax layer. So we know already these layers how they work, right? And encoder block also, like we discussed, there can be multiple encoder blocks. So that is represented as n times encoder and n times decoder. It can be multiple. So what is the functionality of these encoder and decoder? Encoder actually takes the input text and it generates the features. These are actually some features. We don't know what is happening inside, but just assume that it actually gives some features from the input text. Now decoder doesn't take this input text. Decoder is actually for generating the text. Okay, so decoder takes the last predicted words and generate the next word. Suppose in the first case there is nothing going as input and it predicted as how. In the second case, how will come here and it goes as input here and it will predict R. It will go on like that. Okay, so the decoder actually takes the last or previously generated words, and also it takes the input from the encoder, these features from the encoder, because if you are doing language translation, we need some information of this, right, to predict what is the next word. Okay, so it takes the features from the encoder, at the same time it takes the previously generated words and it generates the output text. So out of encoder and decoder, encoder takes the actual input and decoder is the one actually predicts the text. This is the architecture. Now let's go some more deeper into this. This is how the decoder works. Decoder, in the initial there will be nothing. It predicted how. In the next stage, this how will go as input here to the decoder and it will predict R. In the next stage, this will go as input to the next phase and it will predict U. So the decoder works like this. It takes input from the encoder, which is embeddings. At the same time, it takes the previously generated word as the input. And this is during the inference, if you are predicting. But what happens during the training? This is how it looks during the training. Any deep learning model, training involves ground truth as well, right? That means you need to give both input and output to the model. So here also, in case of training, we give input as well as output, both of them to the transformer model. But inputs will be going to the encoder and outputs are targets, right? Ground truth goes to the decoder. In case of inference, there is no ground truth, so it will only look at the previously generated words. But in case of training, it actually looks at the ground truth as the input. Okay, so this is the small difference between training and inference in the decoder functionality. Okay, now let us see what are the modules available in this encoder and decoder. So this is a simple encoder block and this is a decoder block. In case of encoder, we have two blocks. One is self attention, second one is feed forward. Feed forward means it is a fully connected layer. This is actually a fully connected layer, FC layer. So here also feed forward is FC layer. So this we know. Self attention is something new in the encoder. In case of decoder, we have self attention. This is same as our encoder. And we have encoder-decoder attention. So there are two attention mechanisms, two type of attentions in decoder and only one type of attention in encoder. So why is this having an additional attention? This might be encoder-decoder attention. That means previously we saw the output from encoder goes to decoder, right? So this module might take the input from the encoder. This is just an assumption. So in total, in encoder or decoder, we have self-attention block, encoder-decoder attention block, and feed-forward layer. Feed-forward layer, I'm not considering here because we know how it works. It's just a fully connected layer. Now we need to see both self-attention and encoder-decoder attention. So listen carefully from here. Self-attention is the main building block of the total transformer model. If you understand self-attention clearly, then everything is clear from the transformer architecture. Okay. Now let us look at the self-attention. For the self-attention, what is the input going? Input is actually from the embedding layer, right? So that means embeddings are going as the input. What is the output we need from self-attention? Output also we need embeddings, but contextual embeddings. That means instead of general embeddings where embedding layer will give just a unique representation for each word, we need to have contextual embeddings where each embedding will understand or represents how close it is to the other words. Okay, suppose you take this example. Now before passing to attention layer, this particular it might have a generic embedding vector, because that embedding layer doesn't understand the whole context. It will only understand the semantic meaning but not the context. It knows what it is. It is a pronoun or it is referred to a particular subject, like that it can understand. So this it and this it both are same for embedding layer. But according to these sentences, both should be different, right? So this contextual embedding is actually learning that. So this contextual embedding for it will be different here and here. So the output of it will be different for both these sentences. That is what contextual embedding is. Self-attention's main purpose is to convert these input embeddings, whatever the general embeddings coming, into the contextual embeddings. Okay. So in simple terms, when processing a particular word, it decides which other words in the sentence are important or relevant to that particular word. Suppose it is processing it. When it is processing it, it will actually understand, it will actually give weightage to all the other words in the same sentence, and it will give weightage which words are important. This red color indicates actually the weightage. Okay. The darker it is, the more weight it has. So it gives weightage to the relevance of that particular word with all other words in the same sentence. So remember, it is in the same sentence. This and this both are actually same sentence. Okay. It is just checking the relevance of each and every word from the other existing words in the sentence. So it can be looking at the to this like this. It is just like a fully connected layer. Okay. It is just like an FC layer where the input nodes and output nodes all are interconnected, and there will be weightage for each and every connection, which gives the relevance or importance of each word. Okay. And what exactly happens in FC layer? We know that it's a dot product, right? The similar concept happens here. It actually performs the dot product of these embeddings. It's a vector, right? Each word is represented by the vector. So you can actually perform the dot product of this vector with some other vector of maybe Hungary, right? So I can perform the dot product of these two and I will get a scalar. So usually these two dot products will give me scalar, which is a value, which is nothing but the weight of this connection. Okay. So it actually captures the relationship between the words in the same sentence. As it is in the same sentence, that is why the name self came, self-attention. Why is it self-attention? Because it is not looking at a different sentence. You are not comparing two different sentences. You are checking in the same sentence different words, how they are related. So that is why it is self-attention. Okay. So in simple terms, self-attention actually captures the relationship between the words in the same sentence. It does that by using dot product. That's it. It performs dot product and it will give weightage based on the importance. Automatically, when you do dot product, similar things will give high weightage, which are far from each other. The vectors which are far from each other will have low weightage, right? So that kind of computation, it happens. So in its simple form, I'm not going too detailed into this, how it actually do that dot product and what are the other intricacies it has. I'm not going in detail into that because that will take a lot of time. So let us understand this with a simple analogy. Okay. It's like self-attention is just like your group discussion. Imagine that you are in a meeting trying to understand a project. So this is you. You are listening to each and everyone in the meeting room, but you identifies that some people gives good points which resonates with you compared to others. And then from then onwards, you will listen more to those people only, right? So that means you are giving attention, you are paying more attention to a particular person or a set of people like that. So that is what it is. Hope you understood self-attention. I did not go in detail into mathematics, but you understand that it is giving the weightage for each and every word. So the output of self-attention will be the contextual embeddings, and output dimension is equal to input dimension. Both these dimensions are same because we are not modifying anything. We are performing the dot product and then we are using the dot product to multiply the original embeddings to get the contextual embeddings. Okay. Now we understood self-attention. What do I mean by decoder attention? So in decoder, we have encoder-decoder attention. Self-attention actually pays attention to the same sentence, attention to itself. But in case of encoder-decoder, we are having one input from this and one input from encoder. Two embeddings. Okay. Here embedding 1 and here embedding 2. So you perform the attention mechanism, same dot product, same weightage mechanism, but the embeddings are different. Okay. So this is a different embedding and this is a different embedding. So between two different embeddings, you are performing the attention mechanism. That is why it is encoder-decoder attention, because one embedding comes from encoder, another embedding comes from the decoder itself from in the same module. That's why encoder-decoder attention. Otherwise, the computation is exactly the same. Okay. So we have three blocks in total in the transformer: self-attention, encoder-decoder attention, and feed-forward layer. So we looked at self-attention and encoder-decoder attention. So we are not looking at feed forward, it's a simple layer. Now let us see some more details of the transformer architecture. This is the final architecture of transformers. Out of this, we will mark what are the layers we already saw. So input we saw, embedding we saw, self-attention we know, feed forward we know. Similarly, decoder self-attention we know, encoder decoder attention we know, feed forward we know. Apart from this, what extra layers are there and which of them we already know, we'll ignore those. Suppose layer normalization is there in encoder blocks, right? So what is layer normalization? It is similar to batch normalization. So it is a old layer. It's not something new in transformer. Same here. Layer normalization already we know from the previous architectures itself. Similarly here, layer normalization we know, this we know, this we know. Linear layer is fully connected layer, softmax layer we know. So we already know all of this. This encoder block has the same thing as this encoder block. Okay, done. Now, what are the things we don't know and something new here? That is this position encoding for both encoder and decoder. Position encoding is the only layer we don't know and we haven't discussed so far. Now, let us discuss that. What is position encoding? When we discuss about transformer, we discussed one point where the inputs are going parallel. That means each individual word is considered separately, right? So the transformers lose the sequence or position information. They process all the words at once, right? That means they don't know which word comes first, which word comes second. They don't know any of that. If you send like 2000 words also, every word will be parallelly processed and used for that particular task. So it doesn't know the position. Okay. So positional encoding is a very clever trick. This actually helps the transformer understand word order. Okay. So we need to add this information somehow into the transformer. We need to add the information of positions of the word, relative positions of the words into the transformer. Even though we are sending parallelly all the words, we need to somehow add this information. That is where positional encoding came, because the computation happens parallelly, it loses tracks of positions. Now if you see, the cat sat on the mat or the mat sat on the cat, both are same for the transformer, but the meanings are completely different, right? Because there is no position information. Now we need to add the position information. If you see, this position information is being added to the embedding vector, right? Suppose my embedding vector is 512 dimensions. Okay. Now if I want to add this here, my position encoding also should have 512 dimensions, right? Then only I can add these two vectors. So in simple terms, position encoding is also a vector which is of the same dimension as of the embedding vector, but it actually has the position information of each word. What is the purpose of this? It should capture the position information. This particular 512 dimension vector should capture the position information of that particular word. Suppose I took the word cat. Now the cat embeddings might look the same here and here, okay? But the position encoding will be different, because in this sentence cat came at the last and in this sentence cat came in the beginning itself. So even though it is the same word, as the positions are different, the final embedding which is going to the transformer will be different. Okay. So along with the semantic embedding input, we add the position information also to the transformer. Now the question is, what should be this 512 dimension? How can I create a vector which gives me the position information? Because a sentence can have 5 words, or a sentence can have 1000 words, or it can be a book which is having like lakhs of words. I need to have that order maintained, right? Even though I'm having lakhs of words. So how do I create that? And this is a fixed dimensional vector. So every word given to me, based on that position, I should encode that word into a fixed dimensional vector. So what should be this vector? Can I keep it as a learned parameter, just like the embedding layer? If I want the same dimension here, can I keep the position encoding also as a learnable layer? Can I do that? Yes, we can do that. We can learn that. But only thing is, this is not anything to do with the semantic information, right? This is only the position information. Even if it is learned during the training, for not seen words, for the sequences which are more than the ones used in the training, it might not be able to work properly. Okay. And also it adds some more learning parameters, again the computational overhead. We just need to note the position information here. So that's why we need a simple computation without any learning process. It should be very simple computation, but it should be able to capture the position information irrespective of the length of the sentence or length of the input you are providing. Okay. In the paper, authors have used sine and cosine functions for this one. Okay. They used the sine and cosine functions, and it can actually give unique position embedding for each word using a combination of sine and cosine. So every alternative, that means two combinations they took. Okay. In the embeddings vector, two vectors, let's say I have an embedding vector of 4 dimension. So the first two is considered, and for the first one sine will be applied, second one cosine will be applied. Similarly, the next two will be considered, and for the first one sine will be applied, next one cosine will be applied, like this. If this is an embedding vector, let's say you have 4-dimensional embedding vector, the same dimension you are taking. Here you don't need to take the actual entry, right? You need only the index, because we need only the position information. So you need only index here. So it takes the index here. The first one, it applies the sine. Second one applies the cosine. That's why if I take index as I here, for 2i it will apply sine. For 2i plus 1, the next position it will apply cosine. Okay. Why does this work? Is there any guarantee that this will have unique embeddings irrespective of the length of the words? If I have like lakhs of words also, is there any guarantee that every position will have a unique embedding vector? Yes, there is a guarantee for that, because sine and cosine combination, they never repeat at the same time. Okay, the same value of the cosine or sine values, they never repeat at the same time, because for the sine we are giving some x as the input. This x won't be the same for all the positions. For every position this value will be unique, because you have multiple entries here. One is d, which is the dimension of your vector, maybe like 512 dimension, and one is I. In that dimension, what is the position? Suppose you have 512 dimension. In that dimensional vector, first position, second position, third position, fourth position, that is actually I. And then in your words, let's suppose you are having cat sat on mat. In your words, this position is actually what is the position in that particular word. Okay, like second position, like that. For that position you have 512 dimensional vector, and for each dimension you have a separate value. So for this particular word, for this particular second position, for the position and this particular entry, you have two values. For the same sat, for the next two entries in the 512 dimension, you will have different values. For the same sat, for the next two dimensions, you will have different values, like that. Okay, let me explain this in detail. Suppose I have a sentence, cat sat on the mat. Okay, and assume that my dimensions, okay, dimensions is equal to 6. For simplicity, I'm taking the dimensions is equal to 6, and these are the positions, position 0, 1, 2, 3 and 4. For each position I need to calculate the equivalent embedding representation, right? Equivalent representation for position encoding. So now suppose I am calculating the position encoding for cat, that means position 0. Okay, and then for position 0 I have 6 entries, right? Because every position has 6 dimensions in the positional encoding. So these are the 6 entries. Now what I do is 2i, that means two blocks I am considering at a time. Okay, for these two blocks, the first one I will consider sine of whatever the entry is there, right? What is that formula? It is actually position 0 divided by 10,000 power of 2 times I. What is I here? I will be, it will be ranging from 0 to 6, right? I ranges from 0 to 5. So this is actually I value. So initially I is 0, okay? And divided by how many dimensions are there? 6 are there, right? So this will be 0. So 10,000 power 0 will be 1. So 0 by this one will be 0. So this will be finally 0. Sine of 0, right? Sine of 0. So this is 0. Similarly, I want to do position encoding for the same cat. Okay, 2i plus 1. That means the next position for this one. So this is 0. So this we got 0. Now for the same thing for the next position I'm doing here, which is cosine. Cosine of same thing, right? This computation will be the same. So that means this will be 0. Cosine of 0 is 1. That means this will be 1. Okay. This is one set. So I actually is going from 0 to 5. But actually we are taking this 2i here, right? Automatically the next case will be sine of position is 0 divided by 10,000, 2 into 1 divided by 6. Okay. automatically 0 by this one will be 0. So this will again be 0. And for cosine, this will again be 1. So that means this position is 0 again, this position is 1 again. Similarly, this position is 0, this position is 1. This is for the first position. Okay. Now similarly, for the second position also, for the second word also, I need to create a vector, right? For the second word also, I need to create a vector. This is for sat, suppose. This is for cat. Okay. For the second word also, I need to create a vector. Here, the position value will be 1. So that means PE of 1 comma, let's say 2i. And here sine of 1 divided by 10,000 and 2 times 1, okay, divided by 6. So this value will come something. So by doing this computation, you will get some value and you will keep it here. And the next thing is same with cosine, and you will keep that value here. So like that you will calculate for all the I values, okay, for the second word. Similarly, you do for third, fourth, fifth word. Like this, you compute position encoding for different words. Okay, so it can actually generalize for any sentence length, because you just need to provide that particular position, and the based on the dimensions you will provide the index value and then calculate this one. Okay, it will never repeat the same thing for same word. Okay, and the uniqueness depends on the dimensions also. So if you are using only two-dimensional vector for representing the position, maybe you might get repetitions. But if you are using higher dimensional vectors like 500 or 256 like that, then there is very less chance. There is almost like never repetitive. So any two position will never have the exact same pattern across the 512 dimensions. If they are very close to each other as well, at least in one point they might be different. That means out of this 512 vector, dimensional vector, at least in one point they might be different. Okay, so the embedding vector and this one both are of the same shape, and this works on the indices and give you the unique representation for each and every word, which helps in remembering the position of that word for the transformer. And this is a simple code implementation. It's very simple. So sine and cosine, that's it. So you go till the number of dimensions. This is what we have seen. If you see this here, right, this for loop, this goes till the number of dimensions. Let's say this is 512. Okay, and it actually takes the step of 2. Okay, so this step of 2 indicates, this indicates you take two blocks at the same time, and out of that, for the first position it does sine, and for the second position it does cosine. Okay, for I it does sine, for I plus 1 it does cosine. Okay, that's it. Now let's see some visualization of this positional encoding. So these are the equations. This is the visualization of positional encoding with 10 positions and 5 dimensions. So the columns are dimensions, embedding dimensions are columns, and in the x-axis the number of words. So each color represents different values. So each word is different, even though they are common in some dimensions, but there are some dimensions which are different for each and every word. So there are only 10 positions. That's why we are able to represent them only using 2 dimensions. If there are more words, then maybe you need more dimensions here. For example, this is with 100 words, 100 positions and 256 dimensions. As a vector representation, I plotted as a vector just to see in case of 2 dimension, because we cannot visualize more than 2 dimension here. So I wrote a small thing where I took the dimension as 2 for 4 positions. In case of 2D, these are the vectors, because the 2D vectors you can plot. So you can see position 1, position 2, position 3, position 4. Position 1 and 2 are side by side, so they are near, whereas position 3 is slightly far, position 4 is slightly far. Okay, and similarly for 6 positions, same, it goes like this. Okay, so this is just a 2D representation for the position embedding calculation. So this is how the position embedding works. So two critical concepts in transformers. One is self-attention, second one is position encoding. These two are the main concepts in transformer. Apart from these two concepts, every other component or layers are from the previous architectures. Okay, only new things are position encoding and self-attention. So hope you understood how they work. I did not go too much detail into any of these. I try to explain as simple as possible by giving all the required information, but in the simple manner. Okay. So finally, the transformer architecture is this. Usually this is the diagram you find in all the papers, even in the original paper, this is the diagram. So I just kept both side by side just to see the similarities. Input going to embedding. Okay. Both are going to embeddings, and the position encoding is being added to the embeddings. Same here, position encoding added here. This is the encoder block and this is the encoder block. This is the decoder block and this is the decoder block. In encoder block, self-attention, layer normalization, and here attention, encoder-decoder attention, layer normalization, feed forward network. Same here, attention, feed forward, attention, feed forward. Okay. Only thing is, in case of self-attention here, there is actually multi-head attention here. So the only difference is, in case of self-attention, the attention mechanism concentrates on one particular attribute of that particular word. So if you take this example, which we saw previously, here, these particular weights, whatever we saw here, these weights, what do you think it captured here? It captured who drank the milk, right? This it is referred to cat. That means it captured the meaning of this it and whom it is referring to, right? That's what it captured. Now, if you use only single attention, this is the only information we are capturing from this sentence. We are not capturing any other grammatical structure. We are not capturing any other long range dependencies. So a single self-attention block can capture only one type of relationship. It can capture only one type of relationship. But from a sentence, you should be able to capture multiple types of relationships, such as word meaning can be one, grammatical structure can be one, maybe some other long range dependencies can be one. This kind of dependencies on the previous words can be one. So using a single self-attention is not sufficient. We need to use multiple self-attention blocks, and each self-attention block focuses on different aspects of that particular sentence. One can be meanings, one can be semantic information, one can be grammatical structure, etc. So multi-head attention is actually a combination of multiple self-attention blocks. So this multi-head attention is actually multiple self-attentions. Okay, maybe you have 10 self-attentions or 20 self-attentions combined together into this multi-head attention, and all of them process parallelly. That's why you see this parallel connection. The same input embeddings going to multiple self-attention blocks, and each self-attention captures different type of dependency in the sentence. Okay, so self-attention you replace with multi-head attention, and all of the outputs from this n self-attention layers are concatenated together. So these are concatenated together to form the final output from multi-head attention. Okay, and then you pass it to add and norm. So this is layer normalization, this is add and norm, because it is just a residual connection, so it's nothing but add and norm. This residual connection, this residual connection. Okay, this architecture is same as this, only difference is multi-head attention here. So this is the common architecture you see everywhere, so you should not confuse that. So a transformer architecture majorly consists of encoder and decoder, and in encoder or decoder the major components are multi-head attention networks. Multi-head attention means multiple self-attention blocks. And how a self-attention works? Self-attention works by capturing the contextual information within the same sentence, the word dependencies between the same sentence. Okay, in the same sentence, each word, how it is related to all the other words, that kind of relationship or dependency it captures. It captures that by performing a dot product. Okay, this is how a self-attention works in simple terms. And another major thing was positional encoding. Positional encoding, because a transformer processes the inputs parallelly, so it loses the information of the word order. So we need to add that information somehow. So for the input sentence given, we need to create some kind of vector which can capture the position for each word. We need to give this dimension same as our input embedding dimension, because we are adding the operation here. Okay, so the positional encoding vector as well as the embedding vector will be of the same dimension. And how are we doing this positional encoding? We are using the combination of sine and cosine waves to create the positional encoding, unique positional encoding vector for each and every position. And we saw that it is unique even for longer sentences, because the dimension is bigger. So even though the words are very close to each other, there can be at least one dimension where they are unique. So these two are the key concepts in the transformer architecture: positional encoding and then self-attention. Self-attention is the major functional block, and positional encoding is also equally important. So what are the problems the transformer model solved? One thing is, it solved the serial computation bottleneck. That means the parallel computation of all the words. If you give the whole textbook also, Everything will be processed parallelly provided you have sufficient compute power. And it can capture the context vector because of self-attention module. It can understand long range dependencies because you are seeing everything at once, right? You are seeing the whole sentence, whole paragraph, or whole book at once. So it can actually understand all the words because it is looking all the words at once. So it can understand long range dependencies. Now, because it can understand long range dependencies, you can actually give very huge data sets as well to the model. That is why it enabled large scale pre-training. Okay. So when it is pre-training, this is first introduced in BERT. Later it was used in GPT, Llama, all these things. So the whole generative AI evolution came because of transformer, because it enabled this pre-training. If the transformer model is not able to do parallel computation, we cannot do this pre-training on vast datasets. The specialty of the generative AI models is not only on the model side, the specialty is on the data. You should give the major credibility to the data, because these models, the ChatGPT or Gemini or Llama, these models are trained on huge amount of data. That is the reason they are very capable. So we are able to train on vast datasets because the transformer models enabled parallel computation. So this is the major thing which led to the Gen AI field or Gen AI evolution. And also it has improved all other tasks also, all other NLP tasks, machine translation, summarization, recommendation systems. Every other NLP task, transformers has replaced the RNNs and LSTMs. So that is the greatness of transformer architecture. Hope you understood how it works. In the next video, we will look at the different architectures evolved from the transformer. We will look at the architectures behind these common generative AI models like ChatGPT or Gemini, etc. Thank you.